So as we start to talk about solubility, the first thing I want to do is talk about a saturated solution. So let's go ahead and consider that we have a beaker here, and this beaker is filled with water. So to have a saturated solution, I told you in a previous lecture that you have to have a certain amount of solid also present. So there has to be solid and then also dissolved solute as well. So this is the trickiest part about saturated solutions, is the amount of the solute dissolving is equal to the amount of solute crystallizing. So let's see what this actually means. If you were to consider a saturated solution, so let's say we have our solute dissolved right here, and then at the bottom we have undissolved solute. So this is a saturated solution because both dissolved and undissolved solute are present. If we were to add more solute into here, so if we add more solid into here, what we would see is some of this new solute would dissolve, and as it's dissolving, that same amount will start to crystallize out. And so that's what we're going to see for saturated solutions. The next type of solution that we'll talk about is a supersaturated solution. And this is whenever we have more solute dissolved than at equilibrium. Okay, and this could be to a change in temperature or pressure. So instead of part of this being dissolved and some of it being undissolved in a supersaturated solution, this may all be dissolved. And you can do this by heating, but this is relatively unstable. So if you think about using those reusable hot hands, the ones with the metal disc in them, whenever you pop that metal disc, all of a sudden it starts to crystallize out and you're left with a solid and a large amount of heat is evolved. So let's go ahead and look at the effect that temperature has on solubility. So here what we want to focus on is the effect of temperature on solubility for solids being dissolved in liquids. So as we look at this graph, what we can see is in general, as the temperature increases, the solubility is increasing, meaning we can get more solute dissolved as we increase the temperature. And this should make sense if you think about making a syrup or a rock candy or hummingbird food, something like that. If you want to get more sugar to dissolve in the water, what you're going to do is you're going to heat it. And as you heat it, more and more of the sugar will dissolve, which we can see up here on this curve. So if we look at this graph, there's one notable exception here. And we can see here for cesium sulfate that there's actually a decrease in solubility. We're not going to focus on this too much, but we can just say that this is due to entropic effects, meaning something to do with the entropy. So, but in general, whenever we're looking at solids being dissolved in liquids, we can say that as the temperature increases, the solubility will also increase. So now what we need to consider is, what about gases being dissolved in liquids? What kind of effect will that have? So we need to think about, as the temperature increases, will our solubility of our gas increase or decrease? Well, here's a graph of the solubility of gases and liquids. And what we'll see is methane and all of these gases, that as our temperature is increasing, the solubility is decreasing. So why might that be? Well, we're going to start to overcome interactions between different gas molecules and solvent molecules. And also we can think about, we know that from the ideal gas law, we talked about gases expand as they're heated. So if the temperatures increases, the gas will start to expand, and eventually it will start to work its way up to the top, and then it will leave your solution. So you could think about if you leave a soda out, on a warm day, it will go flat much faster than an ice down soda, and that's because of the solubility of gases. So the last thing we want to talk about today is that effect of pressure on solubility. And this is known as Henry's law. And so what we'll see is the solubility is equal to some constant K times the partial pressure of a gas. So anytime that you open a can of soda and you hear that psst, the pressure of the CO2 is decreasing very, very rapidly. And so that's all that extra CO2 escaping. So our solubility decreases. A more serious example of this would be if you were to consider a deep sea diver that surfaces too quickly, because the nitrogen would be dissolved in the blood at a high pressure. And if you start to decrease that pressure too rapidly, then you can have bubbles form in blood and you can block capillaries and you can have real problems, especially if someone were to get on an airplane. So that's what's kind of known as the bends. So we won't use this equation a whole lot, but what we'll see is K is just some characteristic. It's a constant, and it's going to be related to the solubility, which typically would be in terms of grams per liter or milligrams per liter. And then that would also be per some unit of pressure. So you might have grams per liter atmosphere for your constant, and then the pressure would be measured in atmospheres. So that concludes our discussion on solubility.